Joseph Ward Moody grew up in Delta, Utah, in the central part of the state. As a youth, he worked on a farm where he, in retrospect, says that he's very grateful for that farm teaching him how to work. He credits many long nights irrigating, looking up at the dark, clear skies filled with stars, for being the spark that launched him toward a career in astronomy. His sister used to tease him that she could never carry on a conversation at night with him because he was always looking up at the sky. After a missionary service in Japan, he earned a bachelor's degree in physics at Brigham Young University, and then a PhD in astronomy and astrophysics at the University of Michigan. He specialized in the study of galaxies and their distribution through space. He joined our faculty in 1990. He and his wife Cindy are the parents of 6 children. He met Cindy at BYU in a family home evening group. Does that sound familiar? His parents also met at BYU, as did his grandparents. We've served that family extremely well. His great-grandfather also attended Brigham Young Academy, and this year 3 of their children will attend BYU in Provo or Idaho. He is a loyal cougar. They say if you cut him open, he bleeds blue. His talk, entitled Exploding Stars, Expanding Universe, is about the most recent advancements in the study of the nature of the universe as a whole. We will now turn the time over to Professor Moody.
Thank you, President Bateman, for that kind introduction. I am humbled to have the opportunity to take some of your time today to teach you a little bit about the universe. Our understanding of it is currently undergoing a profound revolution, and that is why I was asked to give this talk. But I'm no fool. I know your thoughts are not on cosmology as much as they are on more immediate things like the good weather, the approach of the end of school, and, I trust, finals. With that thought, let's have some fun for just a moment. When I was a student at BYU in the 70s, the Daily Universe published a cartoon of a typical final exam with questions from engineering, sociology, biology, and astronomy. Here's the engineering question. The disassembled parts of a high-powered rifle have been placed in a box on your desk. You will find with it an instruction manual printed in Swahili. In 10 minutes, a hungry Bengal tiger will be admitted to the room. Take whatever action you feel appropriate. Be prepared to justify your decision. For sociology, estimate the sociological problems, if any, that might accompany the end of the world. Construct an experiment to test your theory. For biology, you have been provided with a shoebox containing in powdered form all chemicals necessary to sustain a living organism. Create life. Explain the effect this life form would have had on the English parliamentary system had it evolved 500 million years ago. And finally, for astronomy, it was define the universe, give 3 examples. That's the perfect place to start my talk because it's exactly what I am going to do. Now, the universe is everything there is, of course, simple part. All planets, stars, matter, energy, space, people, etc. And it is governed by natural laws. Consider the law of gravity. What goes up must come down, or more explicitly, everything with mass attracts everything else that has mass. Now, we've known this since the days of Newton, and you've known this your whole life, but it has had several mysteries to it. One is that because gravity only pulls, the universe, made up of massive stars and galaxies all pulling inward, ought to collapse in short order. It clearly hasn't done that, so even back in Newton's day, there was a hint that there must be more to the forces in the universe than gravity alone. I repeat, gravity just pulls in, but the universe doesn't collapse. Has that ever bugged you? I didn't think so. Great minds have struggled with this dilemma for centuries. Finally, Albert Einstein introduced an idea called the cosmological constant. This, in essence, was another force which pushes things apart just perfectly enough to balance gravity over large distances. It was a bold idea, and even if you didn't like it, who was going to argue with Albert Einstein? Then came the 1920s. Unexpectedly, it was discovered by Edwin Hubble of Hubble telescope fame and others that the universe was expanding. This expansion began in a fiery genesis, first derisively, then fondly called the Big Bang. So what do we mean by an expanding universe? What's expanding? Are we getting taller or fatter with time? Well, maybe fatter, but you can't blame it on the universe. It means galaxies, not stars or anything else, just galaxies, the very large entities, are getting farther apart with time. Now, behind me on the screen is a clip of 4 galaxies painted white on the surface of a balloon, and you can see it expand. This is representing a 2-dimensional universe, and I won't go into detail on that, but basically the point of this is to show you that as it gets bigger and bigger, everything gets further apart. It's motion, but it's not motion in a conventional sense. The galaxies move because space between them is increasing. Now, here's a picture of a particularly impressive cluster of galaxies, every one of which is much larger than our own Milky Way. This cluster happens to be moving away from us at approximately 1/6 the speed of light. We estimate that there are at least 50 billion galaxies in the universe, and we have measured the motions of nearly 1 million of them. You know, I wonder, why did God make so many galaxies? I don't know. I suspect we'll find someday that we have a lot of relatives. We've measured the distances or the motions of nearly 1 million of these galaxies, and they're every single one of them, going away from us. In the 1910s, we worried that this meant we were somehow at the center of the universe. Well, mankind once thought that the Earth was at the center of the universe, and we were wrong. We next thought that the Sun was at the center of the universe, and we were wrong again. We're not going to make the same mistake. Our galaxy is not at the center of the universe. Because the universe is expanding, all galaxies are going to see all other galaxies moving away from them, and that's what we witness. Now, to mess with your minds a little bit, I want to point out that there must be a third higher dimension for a 2-dimensional balloon surface to expand into. By extension, there must also be a 4th dimension for our 3-dimensional universe to expand into. This is a natural conclusion, but it does not mean that it's easy to comprehend. To quote Einstein, once you can accept the universe as something expanding into an infinite nothing that is something, wearing stripes with plaid comes easy. Okay? Well, Einstein realized that in an expanding universe, a cosmological constant force was unnecessary. If the universe is expanding, then it has an outward push working against gravity, and the problem of inevitable collapse is solved. The universe might someday collapse, but it doesn't have to. It has other options as well, 3 of them, in fact. So Einstein dropped the cosmological constant from his equations and purportedly called it his greatest blunder. Here are the 3 possible fates of the universe. On the screen, you can see a simple blue line that goes up, bends over, and comes back down. This is choice 1. It says the universe began in a big bang, and it will reach an optimum size, turn around, and collapse in a big crunch, which is we call the closed universe. We hate this possibility. I mean, if someday the universe is going to end this way in a great big collapse, then who cares what you get on your final exams? It's such a pessimistic way, and no scientist or anybody like it. The next choice 2, is that it slows down and approaches stopping as time goes to infinity. This is called the flat universe, and that's the red line on the graph. Choice 3 is that it will expand forever at a fast rate, slowing with time but never stopping. This is called an open universe and is the green line. Okay? So, have you followed this so far? In the past decade, we have finally managed to measure just how energetically the universe is expanding. And you know what? You can forget what I just said. It is none of these three choices. The universe expansion isn't slowing down at all. It is speeding up. Something is pushing galaxies apart faster and faster with time. Einstein's notion of a cosmological constant force looks to be correct after all. Einstein. Even when he's wrong, he's right. Okay, now let me try to explain how we know this. Look again at the slide behind me and notice that each curve has a different shape. If we can determine which shape fits the past expansion rate of the universe, we can decide what the future will be as well. But can we tell what it was in the past? Yes. Because light takes time to reach us, looking out in space is the same as looking back in time. Even better, a photon of light arriving from a galaxy, say 5 billion light years away, will have the signature of 9 billion years of expansion imprinted in it. We can interpret that signature only if we know very precisely how far away it was when it was made, and thus how much space it has traveled through. It all boils down to finding exact distances, which is quite possibly the hardest thing to do in astronomy. To explain this further, let's go to the roof of the Science Center. We're on top of the Science Center looking southwest out over Provo towards Utah Lake. From here, you can get an idea of how far away some of these buildings are. We have the Joseph Smith building behind me, about 100 yards away. Behind it is the New Skin building, maybe a mile distant. Across Utah Lake on West Mountain, we have a tower whose light you can see flashing red. It's harder to guess the distance, but I'd say it's perhaps 20 miles. Now, taking a guess is hardly science. How can we better find out the distances to these buildings? Can we take a tape measure and stretch it from here to there somehow and find the distance that way? I don't think so. There's too many things in the way, and it's not really a straight line to do that. Fortunately, there is a better approach. Look at all the lights out there. Lights are fainter the farther away they are, so we can tell how far away a building is by the brightness of its lights. But wait, is that light over there dimmer than that one over here because it is farther away, or just because it's a lower watt bulb? We don't really know. Well, we're smart people, let's keep thinking. Some of the lights do look quite similar. Those street lights, for example, look the same and seem to be about the same brightness when you stand underneath them. If they are the same wattage, we can just measure how bright they appear to us here, and from that infer their distances. To put it another way, I light a candle to use as a standard and measure how bright it is. I then light another candle and see that it is the same brightness as the first. Now I get a swift student to take the second candle to the JSB. Using a light meter and a telescope, I can compare the brightnesses of both candles and from that discover how much more distant the second candle is than the first. By the same token, if I carefully measure the brightness of a star whose distance I know, then I can find the distance to a star that is identical to it by simply measuring how bright it appears to me and comparing the two. The trick then is to find which stars in the sky are truly identical. Special thanks to Michael Hunter and his film crew for putting that together, and it was a very cold night. Okay, the task is now boiled down to finding identical stars spread through 10 billion light years of space. Hold that thought while I digress to the mid-1980s, to when I was a student at the University of Michigan working on a PhD in astronomy, advised by a young professor named Robert Kirshner. Bob was a supernova expert struggling with a resource dilemma. Astronomy is a simple, straightforward science. We do our research by looking through telescopes. Telescope time, a scarce commodity for you econ majors, is doled out in a meticulously democratic way. Even at private universities that own their own telescopes, the faculty must apply for time months in advance, get it approved by a committee of their peers, then travel large distances to remote sites and image and analyze their objects for a week or so before returning. Supernova, on the other hand, are stars that explode suddenly without warning, brightening in a few days to their peak brightness, then fading out over a few months. They just don't schedule themselves in advance for our convenience. Among stars, they are rare. Of the 100 billion stars in our galaxy, at most one per decade might explode this way, and nearly all of these will be situated in dusty gas clouds that hide them from our view. So we only expect to see perhaps one supernova in our galaxy every several centuries, and you can't make a career out of that. But supernovae are also enormously bright, so much so that when one explodes, its light is greater than the light from the rest of the 100 billion stars in a galaxy combined. As a result, we can easily see them as they explode in other galaxies up to 10 billion light years away. Behind me is a before and after picture of a star that exploded in a very nearby galaxy in 1987. The arrow on the left marks the progenitor star, which you see in the midst of exploding on the right. This is the only star that we have ever obtained a picture of before it exploded. The next picture is a picture of a supernova in a more distant galaxy. While it looks as if it might be separate from the galaxy, it is really just in its outer regions where the star density is low. When looking at other galaxies, the numbers are in our favor. If, on average, one star explodes per galaxy per decade, then if we religiously examine, say, 100 galaxies, we should expect to find 10 per year. Today, we examine thousands of galaxies on a regular basis and find hundreds of supernovae each year. But in the 1980s, we were not doing that. Most supernovae were discovered by accident or by dedicated amateurs working with small telescopes in their backyards. So we just didn't have a good idea of what they were like. We had never even caught a star in the act of exploding. We always found them after they were weeks or months old, fading out of sight. In the summer of 1983, I was at the end of a long observing run at the National Observatory near Tucson, Arizona. The weather had been overcast, so I was spending more time catching up on sleep and studies than looking at stars. A supernova was suddenly discovered in a nearby southern galaxy. This supernova was the brightest to be seen in a decade and getting brighter. Astronomers the world over had a few nights to try to get a calibrated image of it to see if, in fact, we had finally caught a star in the active stage of exploding. Bob called up and asked if I would interrupt my observing run to get a spectrum of the object so we could identify which type of exploding star it was, and of course I agreed. Now, a spectrum is a measure of the brightness of a star in each color of the rainbow. With a spectrum, we could measure the exploding star's chemistry and energy to help figure out why it detonated. The task at hand was difficult. The object was in the southern sky, very low on the horizon. There were perhaps 15 minutes after sunset before it disappeared from sight. I was honored, quote unquote, to be using the oldest digital spectrometer on Earth. A real breakthrough in its day. It was a dinosaur that was terrible to use. Sticking out 6 feet from the back of the telescope, it was made from military tank sights, 35mm camera optics, and a digital detector developed to send AP photos over telephone lines. It flexed so much that as the telescope roamed about the sky, the spectrum would drift completely off the detector every hour or so if we didn't manually realign it by twisting knobs on the end while looking at the image on the detector through a very small eyepiece, also at the very end. Okay, that's the scene. Excited and anxious, I bent the telescope over to the position of the supernova and began the alignment procedure in twilight. Never designed to look that close to the horizon, the back of the telescope with those all-important alignment knobs and eyepiece was now 15 feet off the ground. We had a stout metal ladder on wheels of the type you might see at Home Depot, but it was not 15 feet tall. I climbed the ladder and gingerly stepped on top of the metal guardrail at the top. I was still 2 feet short. Well, looking around the observatory, I found a wooden chair, which I placed on the top of the guardrail and ever so cautiously and stupidly climbed on top of it. It was more stable than you might guess, but it still left me 2 inches short. So tiptoeing on the chair, on top of the guardrail, on top of the ladder, with nothing to steady me. I couldn't even touch the spectrometer, much less lean on it, or it would flex and ruin the calibration. I slowly and successfully aligned the detector. With shaky legs and a focused mind, I slowly descended off the chair, off the rail, and down the ladder. With a huge sigh of relief, I pushed the ladder quickly back towards the wall and out of the way. So relieved to have not fallen off that acrobatic stack, I completely forgot about the chair, which came tumbling straight down, smacking me flush on the head. I have no memory of when it hit me. I only recall picking myself up off the cement with a splitting headache and an extremely sore neck. I was all right, just grateful that no one was there to laugh at me. Well, I obtained a spectrum of the supernova, which was, in fact, still brightening. Here's a trace of it. The line represents the intensities of its colors, with blue to the left and red to the right. And I know this makes no sense to you, but darn it all, I went through a lot of pain to get it, so be respectful. What you are looking at is a classical signature of a gigantic explosion, trust me. Yet still, it is unlike any that had been seen before, missing the very fundamental element of silicon. Other astronomers confirmed this oddness. It was discussed at a special session of the American Astronomical Society and eventually called a supernova type 1b. This discovery was a large step forward in understanding how different supernovae are. Well, I had the privilege of observing many supernovae for Bob in my years at Michigan. Astronomers finally started automated supernova searches, and we began to catch more and more in the act of blowing up. And we learned that there were at least 4 different types. We call them types A, B, and C, 1A, B, and C, and type 2. Now think back to those lights from the film clip. Looking out over Provo, we saw lights of different wattages. Well, a supernova type 1b is essentially a different wattage than a type 1a or a 1c or a 2 or any of the categories that we have. And the question then was, could any one of them be this set of identical stars that we are so desperate to find? What is a supernova? It turns out that all but one type are huge stars that have hurried through their lives to a catastrophic end. Having short lives, they die close to where they were born. Here are several pictures of places where they might be found. This first one of my all-time favorite pictures, is of a nebula in a nearby galaxy, a very close one. The nebula, that's Latin for gas cloud, and that's the beautiful red and green hues in the upper left. In the lower right, you can see a star cluster that's emerged from there. In that star cluster, you have stars of all different masses. Now, the ones that are huge, the very, very bright ones there with a lot of mass, are the ones that will go through their lives very quickly and explode, and they'll explode about right where you see them. Go on to the next slide. This is, again, another gas cloud, and I show you this one to show you the variety that exists in gas clouds out in space. To the left of that, you see a little piece of it that's broken off, and embedded inside that are stars that are still in a cocoon stage. They will eventually emerge, and if they're low mass, they won't explode, but if they're high mass, they will explode, and again, they'll explode very close to the same location. Go to the next slide. Now, this is also a nebula, and you can see right in the middle of it is the remnant of a star that exploded. Go to the next slide. I'll zoom in on that. This 3-ring structure is what is left over from that star. It was the first one I showed you that exploded in 1987. It's not really typical of what exploded stars look like, so I'll go to the next slide and show you something that's much more typical. This is called the Crab Nebula. It's a star that exploded, and the Chinese recorded it. They recorded that it was so bright that it was visible during the day for 2 years, and it went off about 950 years ago. And it looks like a mess, doesn't it? It looks like a star blew up. Well, those beautiful gas clouds that you saw, to us, they are obscuring junk. Sometimes obscuring a lot, sometimes a little, depending upon the individual clouds. They mess up the brightnesses of stars so completely that supernovas found in such places could never serve as identical stars. But one type, the 1A class, are different. These are small stars called white dwarfs. They have lived long lives and have orbited well away from the cloudy nurseries of their births into clear space. If life were normal for them, they would simply fade away, eventually becoming a dull ember coated with crystallized diamond. But their lives are disrupted by a neighbor. If this neighbor star orbits close enough to the white dwarf, material from its surface will be pulled off and end up on the white dwarf, which will get heavier and heavier until gravity suddenly collapses it inward in a matter of seconds, triggering a massive thermonuclear explosion that tears it completely apart. On the screen now behind me is a composite animation of a Type 1A supernova caught in the act of exploding in a nearby galaxy. It's going to run 3 times. So there you see, as it runs, look at the image. You can see the star brighten and dim. On the upper right, you can see a little trace showing what happens to the brightness. It gets very bright, then it begins to fade off. Down below, you can see a spectrum of it, which changes. We look at the spectrum, and using that as the gauge, we find out where that star was when we caught it and finally got a picture of it. And from that, we can infer exactly how bright it was. Then, knowing exactly how bright it is, we can then tell exactly which stage it's at. In Type 1A supernovae, the bottom line is, we have found our set of perfectly identical stars. The white dwarf grows atom by atom until finally it reaches the perfect size to explode. As long as the universe is ruled in all places and times by the same laws of physics, this size will be the same regardless of where the star is located. As a result, every white dwarf explosion will be identical to every other one to a precision greater than the accuracy inherent in 100-watt light bulbs. When this was discovered, Bob Kirshner and students now at Harvard searched for Type 1A supernova as a team, while a rival group at Berkeley did the same thing. Now here's a series of pictures illustrating one of the supernovae that they found. It started with an image of the northern sky as you would see it at night. It's going to go through it twice in case you didn't see it at the beginning. So just watch it as things unfold. It keeps zooming deeper and deeper into space. Finally, we're going to zoom in on that reddish galaxy there, and then right there we're going to have a picture of a star exploding. That's actually a whole lot better than it looked. Now try again. So you got the Big Dipper there, just going past that. The stars of the Big Dipper are hundreds of light years away, and then we're going past galaxies that are perhaps millions of light years away. And then on to galaxies that are actually billions of light years away. This is the furthest supernova we've ever seen. Now, here's the punchline. To everyone's astonishment, the peak light was fainter than expected by 25%, which is a lot. In other words, since it exploded over 5 billion years ago, space between us and it has increased by 25% more than we would have expected for the most energetic of the 3 expansions we considered. The only way to explain this is if the universe is actually expanding faster with time and is not slowing down at all. It's the orange line on this graph. Look at how it bends up and goes towards being off the top after a few tens of billions of years, signifying that the expansion will, theoretically anyway, someday in the far, far future, become infinitely fast. In announcing the discovery, Bob, in characteristic fashion, stated that even though he didn't know why, in his heart he knew he had to be wrong. But after hundreds of supernovae have been examined, it is looking like no mistake has been made. The universe is expanding faster with time. Finally, this animation illustrates exactly how we think the expansion has proceeded, and it will go through twice again. So enjoy this first time through, and I'll narrate the next one. You have the Big Bang. Then it slows down, and then slowly at first and faster, picks up speed again as the cosmological constant force kicks in, eventually running away in an infinitely fast expansion. For Einstein's notion of a cosmological constant force to be correct, there must be some sort of force stronger than gravity expanding space faster and faster with time. Gravity fights it at first, but loses in the end. The energy of the force must make up 70% of all the essence of the universe, and it must grow with time as space expands. Well, I personally wonder if that interpretation will hold up. The universe eventually expanding infinitely fast seems unreasonable. But having it emerge from a big bang at the beginning sounds unreasonable to me too. And we just have to be true to what we see. We're scientists. Having it expand faster and faster also violates the law of conservation of energy, which is one of the foundations of physics. We also have no idea where this force is coming from or what its nature might be. So does that mean that we ought not to trust it? Absolutely not. Rest assured that all these things are something that people will be exploring very hard in the future in hopes of understanding better. And the observational fact that the universe is expanding faster and faster with time looks very, very solid. And any future modifications to our theories of the universe must take that into account. In 10 years, a satellite will be launched to measure supernova brightnesses with a much greater precision than we are able to do now. Follow it in the papers. Maybe it will confirm what I just said. Maybe not. Whatever the result may be, marvel with the rest of us that something as profound as the fate of the universe can be explored by simply measuring the brightnesses of identical stars. Thank you.